Hello physicists, welcome to the fifth and final video in the derivation series. You'll notice, if you're observant, that I'm smaller than normal. This is because the kinetic theory one is the longest and trickiest and we were just going to run out of board space. So this is a modified version of the PowerPoint you've seen in class. Three things you need to be able to do. You need to know the assumptions of the equation, you need to know where the equation comes from, and you also need to be able to use the equation. We're not going to bother that third part, we'll concentrate on the first two. Next slide is going to remind you of the terms that we've used before. There they are. You can pause the video if you need to remind yourselves. On we go. Okay, so we're going to look at how we can work out the kinetic theory equation. And the first thing to make sure that we know is that the speeds of these particles are distributed. So they're not moving at the same speed. Some are fast, some are slow. There's a kind of average there. And it turns out that if you've got a hot gas, then you'll still have the same number of particles. The area under that curve, incidentally, will be the same, but the distribution will be kind of shifted across. So the way that is, but yeah. Left and right is tricky. Yeah, shifted across towards the faster speeds. It's still a distribution. In the derivation, we've got this kind of setup where we've got loads of particles moving around. Each particle will have some sort of velocity in the x, y, and z direction. We're going to begin later on when we start by looking at one particular particle in one direction, and then we'll expand it to all particles in all directions. And we're really looking at the force that they're applying on the walls. We can get the pressure from that. Okay, here we go. Right, so in order to get this, we need to understand the root mean squares. Speed, it's a form of average, as hopefully you remember, and the clue is in the name. It's the root of the mean of the squares. So we are going to add up all the squares of the speeds, where C1 is the speed of the first particle, C2 is the speed of the second, etc. You square them all, you add them together and you divide by the number, so that's basically the mean of the squares, and then you root the mean of the squares. That definition is going to become important later on. So here's our expression that we're going to be looking at proving. PV is a third n mc/ms squared, the kinetic theory equation. That one there. Here are your assumptions. These are really important, they come up in the exam. First off, we're going to assume that the particles are point molecules. In other words, their volume is much smaller than the volume of the gas itself. So much bigger gaps in between them than the size of the particles themselves. That double less than sign means much less than. No attractions between the molecules. If you've got a particle moving towards the side of a container, just about to hit the container, if it's attracted to the other molecules, it's going to have a big force pulling it that way, which will slow it down before it hits the side. Not so much of an issue as it's moving around in the middle because it's being attracted from all different directions, but at the edges, you've got an issue. So no attraction between the molecules, that's point number 2. Point number 3, continual random motion. That is motion which is continual and also random. Number 4, elastic collisions, so we're not losing any kinetic energy to the surroundings in any way, the energy remains constant. Individual particles can slow down, but only by transferring some of their kinetic energy to other particles. And the 5th one is that the collision time is going to be much less than the time between the impacts, and it turns out that these assumptions are all fine for the vast majority of the gases. Only becomes a bit of an issue when you start compressing them to a huge extent. If you compress them, then the volume of them becomes significant and the collision time isn't all that much smaller than time between the impacts and all that kind of thing. So we've seen our assumptions. We're going to start off with this bit here. We're going to look at only one particle to begin with, ignoring all of those. We should also ignore, let me see if I can find a laser pointer. For some reason this little fella here managed to escape the wrath of my black pen. We're only interested in this one here. So it's got a velocity in the x direction, which we'll call u1. It's got a component of its velocity in the y direction, we'll call v1, and a component of its velocity in the z direction we'll call w1. And initially we're only going to be interested in one particular direction. There we go, so there's our situation. It's got a mass of m, it's in a box Lx by Ly by Lz, and we've just already talked, haven't we, about those directions there. Okay, and it turns out that using trigonometry, or Pythagoras I suppose would be a better way of describing that, the square of the speed is going to be equal to the sum of the squares of its components. You've seen that a lot in 2 dimensions. It's also true in 3 dimensions, in case my voice got cut off there. The momentum change of the particle. It starts off as plus m times u1, because mass times velocity is momentum, isn't it? When it bounces off the side, let's see if we can bring our hand into the shot. As it comes in, if it's got a velocity of u1, it's going to come off with a velocity of minus u1, because we're not sliding down. The kinetic energy isn't lost. So it starts off with a momentum of plus mu1, ends up with minus mu1. The difference between those two is going to be minus 2 mu1. That is the momentum change for the particle. Later we're going to consider the momentum change for the container. There we go. So we're thinking about the force on the particle. We already know the momentum change of the particle is minus 2 mu1. If we take the momentum change and we divide it by the time taken, that will be force, because force is the rate of change of momentum. Time taken is going to be basically taken from your speed is distance over time equation. So if I want to know how long it takes for my particle, hands are hard, for my particle to go all the way there and all the way back again, or more specifically I suppose if it collides here, it's going to go all the way there and all the way back. The time between the collisions is going to be equal to distance divided by speed. The distance is twice the length of the box, and the speed is just u1. So the time is going to be 2lx over u1, and as we've already said, the force is going to be the change in momentum divided by the time taken, and you can see the equation there, minus m u1 squared over lx. That there is our force on our particle. There's an ostrich. So there's our force on our particle. We can then work out what the pressure on the wall is going to be, because if we know the force of the wall on the particle is minus mu1 squared over lx, which is what we saw there, then the force of the particle on the wall is going to be the negative of that. So it's going to be positive mu1 squared over lx. There's a derivation bit there. So now we know the force on the wall. We can work out what the pressure is going to be, because the pressure is going to be the force over the area. So we've already got the expression for the force. We're going to divide that by the area. If you remember from before, we're moving in the x direction, so along Lx. So this size of this wall here is going to be Lz times Ly. So the area is Ly Lz. So we're going to take the pressure equation, which is going to be this force divided by Ly Lz. We'll notice Lx Ly Lz is just the volume of the box. So we end up with this expression here. The pressure from one particle in one direction hitting one side is going to be mu1 squared over v. So now we've got that, we need to be able to extend that to all the other bits. So we're going to look at n molecules, and then we're going to look at what happens if we take that in all directions. So 1 molecule's pressure is this, mu1 squared over v. So if I've got another one, the second particle, it will be mu2 squared over v, and if I add them all together, I'll end up with a total pressure, won't I? So I'll have mu1 squared over v plus mu2 squared over v plus mu3 squared over v, etc., all the way up to n particles. I can take the m over v out of that. There's a nice cream there. And m over v is out of there, and then that just becomes the sum of the squares of those velocities. Now, if I look at this bit here, I know that if I was to take u bar squared, that would be basically the mean of the squares, wouldn't it? It would be, if we added all the squares of the speeds together and divided by n, that would give me u bar squared. So if I multiply both sides by n, I find that n u bar squared is the same as basically this entire bracket here. So I can therefore describe the pressure from n particles as nm u bar squared over v. And there we go. Now we kind of need to extend and broaden it out a little bit, because we've now worked out the pressure in the x direction. By the way, if you're thinking we haven't really, because we've only worked it out for one side, that's kind of true, but I suppose if you think about it, if we take this other side into account as well, that's also going to have the same pressure on it. You've got twice as much force if you take the second side into account, but twice as much area as well, so it's not going to affect it at all. So what we've got is we've got the pressure in the x direction. You do exactly the same for the y. You end up the pressure of the y in direction is nm v bar squared over v, and the pressure in the z is nm w bar squared over v, and those are the three pressures. If we want to work out the total pressure, we're going to add those three pressures together and then divide by 3, because your area has now become 3 times as big if you're looking at a cube, and the same logic will work if you're not looking at a cube at all, but at the moment we are. So the total pressure is nm u bar squared plus v bar squared plus w bar squared all over 3v. We just kind of added the 3 together and divided by 3. We found the average of all of those. And the exciting thing is that when we look at u bar squared plus v bar squared plus w bar squared, that's just the square of the RMS speed. Because you remember the RMS speed is just the square root of the barred squared speeds. So we can take this rather ungainly expression here, and we can express it as a third n m CRMS squared. That's our equation, which is what we were trying to prove in the first place. At some point I'm going to learn how to press buttons. No? Okay, that was definitely the computer's fault, not mine. There we are, so we've proved the kinetic theory equation. Isn't that nice? We've figured out exactly why it does the way that it does. Why is this not working in any way, shape or form? On with you. Ah, there we go. There's a lot of effort for a smile on a cat. The last bit we need to do isn't sort of strictly related to the, well, it's related, but it's not deriving specifically that kinetic theory, so it's probably not as relevant, but we're going to do it anyway because it's fun. Mean kinetic energy. Mean kinetic energy is going to be if you take the kinetic energy of each particle, add them together and divide by the number of particles. Obviously, so this one here is half mc1 squared, that's the kinetic energy of the first particle. That's the kinetic energy of the second, that's the kinetic energy of the third, that's the kinetic energy of the nth. Divided by n, that will give you the mean. And you'll notice we can take the m out of that, and you'll notice that this is c1 squared, c2 squared plus c3 squared, etc. And then divided by n, which is the same as CRMS squared. So that gives us the equation for the mean kinetic energy is a half m CRMS squared. Okay, so at some point it would be nice if this moved on. There we go, lovely. Now let's say, for the sake of argument, just for fun, that we assume that the mean kinetic energy is equal to 3/2 times kT. There is a reason for assuming that. We're not going to get into it, but let's just assume it for fun. If we do assume that, we can get rid of the divide by 2 on both sides. We end up with 3 kT is equal to m CRMS squared. We can substitute that expression into the ideal gas equation. Excuse me. Sorry, not the ideal gas equation. We're getting slightly ahead of ourselves. We substitute it into the kinetic theory equation, which is PV is equal to a third n mCRS squared, which is the thing we just proved there, which is there on the board. Lovely. If we sub that in, we end up with PV is a third n times 3kt. If we rearrange that, we've got a third in there, we've got a 3 in there, we end up, you'll notice, with PV equals nkt, which is a slightly rearranged version of an equation you're very familiar with, because of all this bump here. It turns out, there you go, that by that assumption, if we assume that that is correct, then it naturally follows that the kinetic theory equation gives us the ideal gas equation, which is this one here. So therefore it must be true. It must be that the kinetic energy, half mCRS squared, is also equal to 3/2 kT, which is helpful. There we go. And I basically said that exact same thing in the last slide. If we've got n moles, then you can just use 3/2 nRT, where R is the molar gas constant and n is the number of moles. And there we are, we're all done. That's it, that is the last of the 5 videos on derivations. I hope they're helpful. There we go.